Okay, so this is the second lecture on the proof of boundedness of the bilinear Hilbert transform using the tool that applies to a few more general cases. And now the second lecture focuses on the part which is called the tree selection. So let's recall what we did in the first lecture. So we reduced the problem of bounding the bilinear Hilbert transform to bounding this kind of bilinear Fourier multiplier. And now, in essence, the multiplier we are studying is characteristic function of a half plane. And this kind of multiplier has a singularity along a line. And now, the first problem in the bilinear analysis is that this multiplier doesn't factor as product of two multipliers, one of which would depend on eta, the other one of which would depend on psi. But it's not of tensor structure. Then, of course, we could try to cut this multiplier into smaller pieces, for instance, using first the Whitney decomposition of the support of the bilinear Fourier multiplier. So we could decompose this set into Whitney times squares or balls. And then for each of those, we could find an adaptive multiplier by using a partition of unity. But now these things, of course, have overlap when you project them. So that's a problem. We could deal this kind of family of squares in case they were somehow avoiding just a single point instead of the whole line. And this was the Koifman-Mayer multiplier. But now, Koifman-Mayer multiplier we handled last time. But now when we would like to do the real problem, the singularity is a line, so we are not Koifman-Mayer multiplier. So we must somehow continue this task of treating more and more complicated operators. So we know the point singularity, now we move to the singularity, which is a line. Okay, and now the plan is that we would like to decompose the form, which is coming from these bilinear multipliers of these adaptive functions to these pieces of the Whitney decomposition. And as it were, the decomposition is not good enough because there is singularity everywhere. So we would like to decompose the form into subforms, and these subforms are supposed to have localization in frequency, but also localization in space. And this additional information of having localization in space is the key that allows us to do more tricks beyond what we did with the Koifman-Mayer. And now the idea is that when we take one of these subforms and we project to one of the functions, we will have a dichotomy there. So either we have kind of Fourier orthogonality or we have LP orthogonality in the sense of disjoint space forms. And this gives us an almost orthogonality property for these different subforms. And this is somewhat involved computation to put these pieces together. So these 2 points here are just the heuristic, and we will make them a bit more. Okay, and now let's recall the overall strategy. So we had 3 points. So today we will choose this decomposition into subforms. This is one major part. Then tomorrow, in the last lecture, we will adapt the paraproduct theory to the phase space, and this is somehow to deal with these subforms. And then yesterday we did already the LP theory for paraproducts. Yesterday and today are independent parts, and tomorrow's part is to put these two ideas together. Okay, so let's start. Just to fix the notation, so we take the weakly decomposition of the support of the multiplier, and we denote by WK the weakly cubes of side length 2 to minus k. And then W without subscript is the family of all of the weakly cubes. And now, this is a convention that I try to follow, that the k as such is the scale in space, and the scale in frequency is 2 to minus k. So when we see WK, we know that we are talking about something that sees the space scale 2 to k, frequency scale not like those. Okay, and now as it were, these are weakly cubes. Don't worry too much about these numbers, they can be changed, and this is just an arbitrary choice. And now, when the weakly cubes are in the role of decomposing the support of multiplier, I will call them frequency boxes. And the projections to eta or side axis are called the frequency intervals. Now, with this terminology, we take the form or the bilinear operator, and we dualize it, and we will write the resulting form like this. And now here we can insert the decomposition of the multiplier using the smooth partition of unity. So we get this sum where each MQ is adapted to a suitable extension of the weakly cube. And when we undo all the Fourier transforms, we can write this on the spatial side as sum over all the frequency boxes, integral, and then product of three convolutions. Okay, so now we have decomposed the multiplier in frequency. Then we would like to do the decomposition in time, in space. And now, given one of these frequency boxes of side length 2 to minus k, as it were, the uncertainty principle tells us that the smallest sets which are essential are the ones with side length 2 to k in space. So we define the dyadic intervals in the usual way, and we denote them by dk. And the family of all dyadic intervals is p without subscript. And now the product of space interval and a frequency box, so that the side length of the frequency box is reciprocal of the side length of the space interval, is called the multiplier or pi. I will use these words interchangeably, but time should refer to product I cross Q1 or I cross Q2, and multitime would be the product of the three. But it will be always clear from the context which of the things we will be. Okay, and now when we have the multiplier which has been decomposed in frequency, we can just divide this sum over all weakly cubes first according to the scale. And then when the scale is fixed, we can divide the real line where we integrate the space into dyadic intervals of side length 2 to k. Okay, and now we have this triple sum, and we have three parameters of summation: the scale, the location in frequency, and the location in the space. And this is somehow the tree space where we will do the selection of trees. Okay, and also if we fix a single term in this triple sum, this is somehow an object which should not have any internal structure. So it has the scales according to the uncertainty degrees. Okay, and then now that we have just using equalities cut this form into small pieces, we should start grouping them into what we will call trees. So let's start with the localization of frequency. So we take a frequency from the singular subspace, which will be now the line, and we will co-subordinate to that frequency all the frequency boxes so that a dynamic by 2 to 100 contains that. So geometrically, what this means is that we draw a cone with certain opening, and the larger this 2 to 100 is, the more wide is the opening. And now being subordinate to the frequency for a weakly cube or frequency box means sitting inside this kind of cone or meeting such a cone. And just a remark, what is important for a good definition of trees is that we will use subordination where the opening of this cone is more than the right angle. So we would like to have something that opens more than 90 degrees. And also another important thing is that this definition of subordination should be somehow blind to these three input conditions. So it should be independent of permutations of coordinates. And then second remark, when we fix a frequency and we take all the tiles that are subordinate to that frequency. Now there is the characteristic function missing, but you can add there. So when we take sum over all tiles who are subordinate to one point, we will actually recover the Boltzmann layer. So this is the frequency localization, and as such, it's good, but if we take these subordinated families, we don't know how to sum them up. So we must proceed and localize these things also in space. And now when we look at the tiles, even if we take a single box here, when we move to the physical space, it can have several different locations. So this doesn't, this picture still forgets what happens in the spatial side. And this is a schematic picture of what's happening. So we have these frequency boxes, and to each of the frequency boxes, we can associate various intervals. Okay, and then comes the core part of the whole thing, namely the definition of tree. And now the idea here is that the definition might look slightly vague, but the idea is that we have the input triple of data. We have this top frequency, psi, who is a frequency living at the singular subspace. This is the frequency. Then we have an interval, I0, somewhere in the space. And this interval contains the information, location, and scale, because the interval has sign. And then the third part we take as an input for defining a tree, or a tree could be called to be this triple, is the finite family of multiplies in which the tree is generated. This will be kind of reference set, and in a way, it will be a way to say that tree knows where it grows, when it grows. And now when we have this triple, the tree is the idea of generating certain objects. We can add anything in this list that we want, but of course now choosing the interesting things here is the art. So the things that we will need to refer to later are first of all the initial data itself, the top frequency, top interval, and the initial factor. Then the first non-trivial thing is the family of tiles that this tree is supposed to take with it or exhaust. So when we draw the singular subspace here, and we take the dot frequency here. Now the idea is that we have two subordination definitions, the one of chosen types and the one of boundary types. So with the first one, namely the chosen types, we choose a big enough subordination parameter and say that we will take everyone here. Okay. So any weakened cube within this opening will be chosen. And those types are in the family PT. And then we have the second subordination condition, which says that of the chosen families, there are the ones which are somehow chosen, but barely chosen. So they are subordinated with one opening, but not another. So here we have the times who are in the bound. And doing this distinction will be important for later part of the argument. And this is maybe somehow this is a part which makes argument much cleaner later, and it's one of the new contributions. Okay, and these were the important things. And okay, later I will also call these ones who were chosen but not boundary, I will call them core types, because they are in the frequency core of the tree. They are very far from anything that's outside the tree. Okay, I still draw here one thing, because we have somewhere holding this top interval, which has a side length. So the side length of the top interval will be telling us that there is somewhere the line that no one on this part will be a chosen type. And now we have the chosen types and we have the bound. And now the idea is that we will later choose trees so that these chosen types will exhaust the form. So as it were, we start with the family of types. We have all the possible trees, and then we want to do clever selection, so that for each amplitude parameter k, we will find a family of trees, so that we can associate a size function, so that the size for inside this family will only see something small. Okay, now this is slightly bad. There should be a subscript, or this right-hand side should be written differently. But the point is that there is a size parameter, which the size function, which associates some number to this family. And then we decompose the whole form into subforms, which come from this choice, which we will do later. And now for these subforms, we must have condition. First of all, we will need the phase space form of the parameter estimate. This is something we will see tomorrow. And in order to get something like this, the definition of the size must be somehow large enough. So it must be strong enough to control the type form coming from the chosen multi-type symmetry. And then on the other hand, the size shouldn't be chosen too large, so we must still be able to sum these things up to get what we want. Okay, so now the next thing is that we should see what is the correct definition of size. And as with the tree, these are very entangled definitions. When you just, start with how do I define a size or how do I define a tree, As such, it's impossible to do, but you must know the argument from the beginning to the end. You must know where these things interact with each other. So I will just give the right answers with the process of trials. Okay, so now as it were, the tree form must be bounded by the size, so it must be large. Then we should be able to control it with L2 and L infinity norms, so it must be small enough. And then there must be this kind of possibility to get orthogonality estimate for the chosen trees. And this is another smallness. And then I just give the definition of the size. And now there are several sizes. So we will split the task of measuring the tree into several parts. So before doing that, let's pick some notation. So rho I will be a bound function at scale of interval I. And sorry, it will be the distance function, which is normalized to the scale of interval I. And then for a rectangle in the frequency space, we will denote by phi and alpha the family of functions who are basically adapted, whose Fourier transform is basically adapted to that rectangle. And now the end is choosing one of these indices. Okay, and the sizes we use are the following. So different parts of the tree are treated with different sizes. So one part is the core part. This is the part of the tree which really doesn't see other trees. But this is also the part of the tree where you can imagine that the part product estimate we need will be tricky one. Because this is the part of the tree where we have this kind of projections overlap. So here we have this missing linearity in one of the variables. So this is a part which is independent, but it will have involved parameters. Then for the boundary part, we will use different sizes. So whereas this first size was not having any mean zero property with respect to the top frequency, these other ones will have. So there is the supremum size, taking just the phase space projections of various pis, and all these pis here are somehow having the zero property with respect to these. And then we have a sum size which just sums over all these space projections on tiles in the node. Okay, this is maybe too much information. If two things must be taken, one is that in the core size, we will not be using any mean zero properties. And in the boundary size, we will have very good mean zero. Whereas the core size doesn't really know the tree. So this is depending very weakly on the tree. As you see, we have just the top frequency, and then we have just functions who are adapted to balls around that top frequency. This is actually no information about heights. We could write this thing without knowing basically any of it. We just have family of inputs. And contrarily, in these other two parts, these are suprema over sizes. So they are very sensitive to that there is stacking. Okay, another partition of the form into trees will be following this kind of lemma, where I have contracted the notation. So we have a constant C, so that if we start with a good family of multiplies, Then for any amplitude parameter capital N, we can find this family of trees Tn and the residual family, so that whichever of these coordinates we choose, and whichever of these amplitude parameters we choose in the trees, in the family of that amplitude parameter, all the sizes we have seen, okay, there are certain indices that are hidden. The size is bounded by that. Okay, so this is an easy thing to do. The harder thing is that we also want these trees to be almost disjointly supported relative to the amplitude. And this is somehow kind of best of that. And then, of course, we would like to see that once we have done all these selections and we put all the types together, we recover the origin of family. Okay, now suppose you have this selection. We can take the original form of tiles and we can rearrange the sums so that we first sum over the amplitudes, and for each amplitude we have family of trees. We sum over the trees there, and for each tree, okay, this is abuse of notation, this should be PT, the chosen types of the tree. We sum over those, and then for each of the types we have the type. And now let's speculate before talking about the tree selection. How do we conclude the proof from this, and what are we still missing? So suppose we could take one of these trees, so fix capital T. We are left in the last. So suppose we could bound this kind of tree product by a suitable product of sizes. Then in the next slide, I will show the computation, how does the things, the proof compute. And before that, just a remark. Now we have sizes on the right-hand side, not the elements that we had from the Wolfram-Mayer types. And of course, it's a huge difference because the size really remembers where in the phase plane the tree is, whereas this has really thrown away all the information about phase localization. Okay, so now if we have this estimate, then there is a computation showing that for these sizes, we have first of all this kind of trivial estimate that we can bound them by one, provided we have bounded functions in as input. And now, for simplicity, let's assume the input functions are characteristic functions. Of course, you must do some approximations to not run in trouble with such rough functions, but for this computation, let's take it like that. Okay, so now if we have this space paraproduct from the previous slide, we can just insert it to this tree formula. And for two of the functions, we will use the bound of the size that we get from the tree selection. So we get bound, and then we will use the properties of the sizes in this and the paraproduct estimate to see this 2 to n over Pn here. So there is an additional step missing, but this is essentially what comes from the tree selection and basic properties of sizes and the correct form of the phase space paraproduct estimate that I get. And then for the last of the functions, we will use this estimate. So we write it as minimum of these two. Okay. And now we will just put all the pieces together. So these things come out from the end sum. When we sum over the measures of the top intervals, we have the second part of the tree selection proposition, which gives us some contribution depending on 2 to n. So it will be giving a factor 2 to minus n. So we will be summing all the integers, and we will be having this kind of function here designed to sum. So it will be k when n grows large, and it will also be k when n goes small. So it is having geometric decay in both directions. So the value of the sum will be the largest term roughly, and this will speak the correct expression of norm L1 L2 norm to power 2 per p. And now, if these functions were characteristic functions, we could bound the triple of norms by this triple of characteristic functions. And this would be enough for a multilinear interpolation function. And that would be somehow the end. Okay, so 2 things remain: the proof of the tree selection and this phase space part. And the phase space part product is left for tomorrow. So let's look at this thing of tree selection. So this is the statement of the lemma again. So we want to have things that are smaller than 2 to n over 2, and we want to have over, and we want to cover. And how you do this, it's a greedy selection. So we just go these coordinates one by one, and we go the sizes one by one, and for each of them, we will do different selection. So first, when we have fixed a coordinate, we find large enough capital N so that any tree has size below the level we want. And this is now possible because we start with defining size. So in principle, we have some upper bound for it. Then we start picking trees in a greedy manner. So if the size is above the level that we will call the next level, we take it and we remove it from the reference family. And then we take this new reference family and we are looking trees with respect to that reference family, and we keep doing the greedy selections. And because we only have finitely many trees, the process will halve at some point. And this is roughly the core argument. But you must do some adjustments for each size, depending on which size you are picking. It is actually this simple for the core size, because in the core size, we are only looking at the stuff that's well inside the tree, so the interaction of the trees is very minimal. But for the boundary sizes, it's more hard. Okay, but as a little idea, this is very simple. You just do greedy selection of the greedy selection, you exhaust them. And now, if you do this greedy selection for every amplitude and for every size and for every coordinate, it's obvious that you will get the properties you wanted, the first one and the third one. The exhaustion and the size. And then the hard one is, of course, the over. And now, the way to look at this is that we first take the sum we would like to estimate. Then we will use the definition of the size and the choice criterion to split this into square roots, the size, and then square root of what that was. Then we choose a function that roughly realizes this size. And now we must have done some preliminary reductions to make sure that, at least talking about the core size, the tile that realizes the size of the tree will be having the scale of the total. So in principle, starting with the definitions we started with, it could be that for this tree, which has size like this, the realizing tile would be someone here. And that would be the problem, because now the expression we have written down here would really have forgotten the actual scale of the tree. And the way to get around this is, of course, that in the previous step, we should have done the choice more carefully. We should have said that, okay, if I cut this part of the tree away, I can take a shorter tree, which has still the same size, and the remainder part I will leave for later. And that's essentially how it's done. Okay, but now suppose we have this kind of nice tile, then we will have this projection, and this is some function doing the tile projection. And then we dualize, we write the L2 norm as an inner product with the dual vector. Then we put the sum inside the pairing, and we do the Cauchy parsing. And now this is somehow square of the thing we would like to control. So when we start estimating this quantity here, we would like to see L2 norm of f and square root of this thing. And then we will divide the square root back, and we will leave. So now, doing this business with Cauchy parts, we get first this kind of slightly lengthy expression. So we are summing over over trees. There is another sum which I now, there's no at the first level. We have this sum, and you see that there are, yes, there are two sums here. The other one is left out, and we are estimating this sum, and the other sum is done later. So the other sum gives us one tree, T prime, and the sum which is visible gives another tree. And now here, what you should see is that we have convolution of the frequency projections. And this is telling you that if the frequencies are far away from each other, this term will not appear. Okay, once we keep this in mind and reduce the family to those where this term is non-zero, we can put all these things to one of the functions, and we can use an additional proposition to pull some of this decay out from these convolutions. Now, when the scales are correctly, you can pull part of this decay out. Now, I have written the same alpha, but lose a bit, but not too much. And then you can control this double convolution by the Hardy-Littlewood maximal function. You can do here Cauchy parts, and then you are left with estimating the L2 norm of this sum. And now there is a lemma which we saw at least in a paper of Muscalutau and Thiele for very similar problem, actually a one-dimensional version of what we are doing, that if you have a family of intervals which is boundedly overlapping, the L2 norm of this quantity has the boundary. So they were doing exactly the same computation. This is exactly the property they need. In their setting, with their sizes, with their stuff, with their pre-selection, they could use it. So now we must check that our choices of things will lead to the same properties. So if we don't have zero from the frequency, we must have disjointness in space. And if that holds, then the proof finishes. And now the idea is that if we have two of these intervals meeting, then the top frequencies must be far away, because otherwise one of the trees, the one who was chosen first, would have taken some ties from the core of the other. And that would be contradiction, because then the other tree would exist, because it was taken earlier. For the core size, it's this simple. And it's now important that there is this security region, which makes it possible to choose this way of defining phi large enough to control all these, but small enough so that it doesn't interfere with the neighboring trees. And this large versus small is where we need really this kind of shifting regions, that the phi we have for the core size, it stays away from the boundary of the tree, but covers the core. And that's why these kind of frequency projections that are taking care of two core parts must stay far away, unless they are coming from trees that are spatially separate. Because if we have proximity both in space and frequency, then one of the trees grows too close to the other. And then there is the other part, that when we are talking about boundary, then these things that appear here in the supremum of boundary types, they will be related to single types, and it's slightly easier. We can say that if two types are really intersecting, then they must be basically doing the same game. And then the last case, which is maybe the hardest one, is the sum size for the boundary. And for the sum size, one must do an argument which is more complicated. We must do a cone decomposition for the space if we are in higher dimensions, or we should deal with the plus and minus directions separately, and we must choose these trees in an order so that we start from larger psi and we go to smaller psi, so that we can do more careful arguments at this point. Okay, so that's roughly the idea. But now there are tons of details which are left out. Maybe one more comment is that one property of these sizes that they must satisfy is that when we add some tiles to the tree, the tile should be the tree should be somehow growing, and this set of three sizes is, at least in our consideration, the minimum we could use so that we can keep this core part as a separate part and then add something to the boundary. And if we remove one of the sizes, then this match is somehow breaks. For instance, for the boundary part, you could try to use only the sum size, but in order to do this argument for the sum size, you will see the other boundary size appearing as a side product of them. So now you have to do some other sum size. But the number of sizes 3 is still relatively small. In older papers, there are varying sizes at once. Okay. So this is the precision I think one can give in short time about this argument. if you want to have it in detail, then you must sit down with me, or preferably try to prove it yourself. This was basically all for today. So just to summarize in 4 points. First, we started with this form, which is sum of many, many types. And we organized the sum into trees. The tree was geometrically in frequency this kind of truncated O, which has 2 parts, the core part and the boundary. The core part is independent of other trees. The boundary part is the one that talks to the other. And then we have to define the size, which has balanced properties. So it must be large enough to control all the phase space stuff inside, and it must be small enough so that we have the bound by the key. Okay, so that was all, and tomorrow in the last lecture I will do the phase space projection and the phase space estimate for the part. And then there we will see somehow that these sizes which work here, although I didn't do the argument, they are very reasonable when we do the parameters. That was all.
Thank you, Olli. Any other questions? No. Let's stop here and then we will see tomorrow.